Did you ever dream of traveling through time? With advancements in quantum computing, this dream might not be far from reality. Quantum computing is a revolutionary technology that holds the potential to solve complex problems exponentially faster than conventional computers. But how does it relate to time travel? Quantum mechanics suggests that particles can exist in multiple states at the same time, a phenomenon known as superposition. By harnessing this superposition, quantum computers could perform calculations that would take current computers billions of years to complete. And with such immense computational power, scientists believe that they could unlock the secrets of time travel. The concept of time travel through quantum computing is based on the idea of manipulating the fabric of space-time. With enough processing power, we could potentially manipulate this fabric and create wormholes and shortcuts through the universe. While this idea may seem like science fiction, scientists have already made incredible strides in quantum computing. Quantum computing represents a monumental shift from traditional computing. Quantum entanglement is a phenomenon where quantum or qubits become interconnected and the state of one qubit can instantly influence another, regardless of distance. This property is crucial for quantum computing, enabling complex computations that are exponentially faster than their classical counterparts. Quantum parallelism, a function of superposition, allows quantum computers to evaluate multiple possibilities simultaneously. This capability is particularly beneficial for tasks like database searching, cryptography, and simulation of quantum systems, which would be incredibly time-consuming for classical computers. There are two major algorithms that govern quantum computing: Shor's algorithm and Grover's algorithm. Shor's algorithm is designed for factoring large numbers and breaking encryption used in digital security. Grover's algorithm is designed to provide a way to search through a database quadratically faster than any classical algorithm. This is significant for large-scale data analysis and unstructured search problems. Quantum computers can simulate other quantum systems more efficiently, which is not possible with traditional computers. Some of the challenges and limitations of quantum computing include sensitivity to external disturbances leading to errors, which makes error correction essential but also challenging. Quantum error correction is a critical area of research, focusing on protecting information within a quantum system from the environment's noise. Increasing the number of qubits in a quantum system is a significant challenge due to error rates and the fragility of quantum states. Quantum computers typically operate at extremely low temperatures, close to absolute zero, to maintain quantum coherence. Bits can lose their quantum state, known as quantum decoherence, which is a major barrier to developing practical quantum computing applications. The theoretical foundations of time travel are deeply rooted in the realms of physics and mathematics, involving complex concepts from general relativity, quantum mechanics, and theoretical cosmology. These theories provide frameworks that suggest the possibility of time travel. Quantum mechanics, with its counterintuitive principles, provides a unique perspective on the nature of time and space, opening speculative pathways to the idea of time travel. Quantum mechanics, the underlying theory of quantum computing, introduces concepts like superposition and entanglement. These principles defy our classical understanding of physics and hint at a universe much more interconnected and malleable than previously thought. According to quantum mechanics, particles can exist in more than one state at once, as the well-known Schrödinger's cat thought experiment illustrates. Erwin Schrödinger, an Austrian scientist, came up with the Schrödinger's cat experiment in 1935. The experiment presents a hypothetical scenario involving a cat, a flask of poison, and a radioactive source inside a sealed box. A cat is placed in a steel box along with a Geiger counter, a small amount of a radioactive substance, and a vial of poison. The amount of radioactive substance is so small that, during the course of the experiment, there is a 50% chance that one of its atoms will decay, releasing radiation and triggering the Geiger counter. If the Geiger counter detects radiation, it will trigger a hammer mechanism to break the vial of poison, which would kill the cat. If no radiation is detected, nothing happens to the cat. According to the Copenhagen interpretation of quantum mechanics, as long as the box remains closed and unobserved, the cat is considered to be simultaneously alive and dead. This is due to the principle of superposition, where the radioactive atom is in a superposition of decayed and undecayed states until it's observed. Only when the box is opened and an observation is made does the superposition collapse into one of two states. The cat is either alive or dead, determined by whether the radioactive atom decayed and triggered the poison. This thought experiment was not intended to be a practical experiment, but rather to illustrate the strangeness of quantum mechanics and the problem of measurement. Schrödinger's point was that it seemed absurd to say that the cat was both alive and dead until someone looked in the box. Einstein's theory of general relativity suggests that gravity is the result of the warping of space and time by mass and energy. It implies that the structure of spacetime is flexible and can be deformed by massive objects. A theoretical consequence of Einstein's equations is the existence of wormholes, which are bridges or shortcuts through spacetime, potentially connecting distant points in space and time. Wormholes could allow for travel between different times and places, but their existence is still hypothetical. Certain models of the early cosmos predict the existence of cosmic strings, which are fictitious one-dimensional flaws in spacetime. The immense mass of cosmic strings could warp spacetime around them. Traveling around these strings could, in theory, allow for time loops, or CTCs, closed time curves. Superposition allows particles to exist in multiple states simultaneously, and entanglement links particles across vast distances. These principles defy our classical understanding of physics and hint at a universe much more interconnected and malleable than previously thought. CTCs are paths in spacetime that return to their starting point in time. General relativity allows for the existence of such curves, which could theoretically enable time travel to the past. The Novikov self-consistency principle, proposed by Igor Dmitrievich Novikov in the 1980s, asserts that any actions taken by a time traveler were part of history all along, thus preventing paradoxes and ensuring self-consistency in the timeline. The concept of entanglement in quantum mechanics, where particles remain connected regardless of distance, opens up speculative ideas about connections not just across space but potentially across time as well. Hugh Everett III's many worlds interpretation suggests the presence of an endless number of parallel universes, which would enable a type of time travel in which decisions made in one reality have no bearing on those made in another. The Typeler cylinder, proposed by Frank J. Typeler, is a hypothetical object that is a massive, infinitely long cylinder spinning at near light speed. According to Typeler's calculations, orbiting such a cylinder could create CTCs, allowing for time travel. Based on our current understanding of physics, such a cylinder would require physical conditions that are considered unrealistic. The theoretical constructs that could enable time travel, such as wormholes and cosmic strings, would require forms of energy and matter that are currently speculative or beyond our technological capability to produce. Quantum computing, with its ability to perform complex calculations at speeds unattainable by traditional computers, offers a potential tool for solving the incredibly complex mathematical models of spacetime and gravity as described by general relativity and quantum mechanics. This manipulation would theoretically create wormholes. Quantum computers could simulate aspects of the universe that are currently beyond our reach, like the conditions around black holes or within wormholes, providing insights into how spacetime could be manipulated. One of the greatest challenges in physics is unifying quantum mechanics and general relativity. Quantum computers might be instrumental in exploring and validating theories of quantum gravity, which is essential for understanding how to manipulate spacetime at the quantum level. Artificial intelligence could play a crucial role in managing the incredibly complex calculations and simulations needed for spacetime manipulation. AI, with its advanced pattern recognition and predictive modeling capabilities, can analyze vast amounts of data from astronomical observations and experiments, potentially identifying patterns or anomalies in spacetime that could hint at natural or artificial wormholes. AI algorithms could analyze patterns and predict outcomes in quantum states, aiding in the stabilization of wormholes. AI can be used to optimize algorithms for quantum computers, enhancing their efficiency in solving complex spacetime equations or simulations. In a hypothetical scenario where spacetime manipulation is possible, AI could be instrumental in navigating and maintaining stable paths through complex spacetime structures like wormholes. Quantum computers and AI could be used to design and run experiments that test the limits of Einstein's theory of relativity and quantum mechanics, especially where they intersect, such as around black holes or in conditions of extreme gravity. Before any real-world manipulation of spacetime, quantum computers could simulate such scenarios, with AI analyzing the outcomes and providing insights into the feasibility and consequences of such manipulation. The current state of quantum computing and AI is still far from having the capability to manipulate spacetime. Advancements in both fields are required to reach a level where they can effectively contribute to this area. Our current understanding of spacetime, especially in the context of quantum gravity, is incomplete. Quantum computing and AI may aid in this understanding, but there is still a long way to go. While the integration of quantum computing and AI holds promise for advancing our understanding of spacetime, actual manipulation of spacetime remains a theoretical and speculative concept. These technologies could one day contribute to groundbreaking discoveries in physics, but for now, they provide tools for exploration and understanding rather than practical application in terms of spacetime manipulation. Thanks for watching. Please remember to subscribe.